All right, recording is rolling. So welcome to Tuesday, October 12th. Come back from a 3-day weekend. So here's the plan this week. Oh yeah, your guys' open notes, take a quiz. I have it ready for you guys. On the right side of your desk. If you reach around the right side of your desk, you guys see a page that looks like this on the right side of your desk. So pick up one of those. This is due 6 days from now. So Monday coming back from the weekend. And then we'll take the rest of it today and solve, well, you know what, not exactly. We're going to finish the textbook problems at a time, you guys. There's just a few more left to go there. But I've also got a Kahoot lined up for you guys later today, too. Okay. So everybody's got the quiz, right? From the right side of your desk. You guys got this quiz? And it says honors on it. Sure. That's all. All right, so tomorrow's the kind of a weird day. There's, of course, PSAT testing. If you have a question where you're supposed to be, let me know. Have an Excel file, I can look you up. Right. Now, since you guys are sixth period, then the PSAT should be over by then, and you guys will meet in this room, but you might have some relocation for your earlier classes. Okay. Now, since tomorrow's going to be kind of a weird off day, I think what I'm going to do is give you guys tomorrow as a space and a time to finish that open notes take-home quiz. I've got some backup activities too, but that'll probably be what most of you guys probably want to do. Okay. There's another lab I'd like to fit in for the end of the week that involves like coins and turntables. So something to do with like this, like spinning around. Guys remember this turntable from Friday? And then anything else I want to throw into you guys? There's got a few days to do that. So that's what we're doing. Oh, and then the homework that I have to finish with you guys today, which is here. You guys remember these problems that we've been working on, right, from chapter 6 and chapter 7? Right. So we finished most of this last week. Just got a few more to do. The due date was this coming Friday, so in a few days. Now, since you guys will be finished with this by the end of this class period today, if you've been following along, then you can turn it in early. That's fine too. Right. All right, so let's do. So the next one we have to do is number 86 from chapter 7. This one right here. 86. Find the value of g, the acceleration due to gravity, in the following situations. So you guys know that at the surface of Earth, this number is pretty close to 10 meters per second squared. It's three questions packed into one. So part A says, what if Earth's mass tripled, but everything else stays the same? Okay. And there's a couple of follow-up questions. So let's just do one at a time. So number 86. Okay. All right. Now, you want to know free fall gravity and how that changes as other things are changing. You know, Earth's mass in this case, but later on some other things. Well, we need an expression, maybe a formula for how does this relate to all those other variables. Do you guys remember it goes like this? Gm over radial size squared, gm over r squared. Yeah, I did take down all the posters just because PSAT is tomorrow, but this is one of your formulas. You guys remember that? All right, so first question is, if you triple the mass, what happens, and you leave everything else the same, then what happens to free fall gravity? Because if you triple mass, what happens to free fall gravity? It also triples. You guys see that? Okay. So hold on to this idea. Let's see, what if you did something like this? So part A, you gotta have, say G nu equals G times 3m over r squared. Okay. Well, I can just pull the 3 out in front. Say G nu is equal to 3 times gm on r squared. This right here is 10 meters per second squared. So 10 meters per second squared for Earth. So the 10 meters per second squared, just substitute that in right there, and you get 30 meters per second squared. Okay. So the relationship is that, well, there's a direct relationship between the mass of the planet and the free fall gravity. Okay. So you triple one, the other triples. Now, part B says, let's go back to just regular Earth, and then now we're going to change something different. What if Earth's radial size is tripled? So we're going to make the Earth, 3 times as big in terms of its radial size, but its mass remains the same, which is kind of a crazy scenario because, well, it wouldn't be made out of the same density material. Maybe it's made out of like very fluffy styrofoam or something. If it's the same mass occupying a much larger volume, that would be good. But let's run the numbers and see where this goes. And so for part B, they're saying, see, G and M stay the same, but now we're going to triple the radial size. Now, don't forget that there's an inverse square relationship between the gravity field and the radial size. So that factor 3 is also getting squared, isn't it? Which means the new gravity field is going to be what compared to the old one? It's not 1/3, it's 1/9, 1/9. Yeah. So new gravity field is, well, take this out in front. 3 squared is 9. It's in the denominator, so 1/9 of GM on R squared. And if all this stuff is 10 meters per second squared, then you're looking at, well, 1/9 of that, which is closer to 1 meter per second squared, maybe like 1.1 something. Yeah. So there's the first two questions. Right? And more what I want you guys to get out of that is that relationship. So the part A was a direct relationship. The part B is an inverse square relationship. Okay. Now part C, okay, so let's go back to the beginning. Part C, both the mass and the radius are, well, your textbook says doubled. Since we've been doing triple, maybe I'll just stick to triple. Right. So what if you triple both? So the classic gravity was your Gm over R squared, came out to 10 meters per second squared. Okay. What if you tripled two different values? This is part C. Okay. So universal gravity constant, that's the same. What if I triple the mass of the Earth and I triple its radial size at the same time? Which, if you think about it, sorry, I'm sorry guys, let me back up here. If you triple the radial size of Earth, I'll let you guys know that anything to do with linear distance, like radius or diameter, well, that would also triple. But the surface area of Earth would actually go by a factor of 9, and its volume would go by a factor of 27. This is a side note, but if the volume's going up by a factor of 27 and the mass is only going up by a factor of 3, then it's still made out of light density material, maybe some kind of like fluffy styrofoam, but sort of side thought. Anyway, back to this though. Okay, so you have these competing effects. I mean, more masses might seem like more gravity, but bigger radial size, by itself in isolation might seem like less gravity field. Yeah, they're going against each other. What's the net effect? What do you guys see? A third overall, because you got times 3 on top, but divide by 9. So if I factor everything out, got a 3 on top, got a 3 squared on bottom, which is 9, times the old gravity. Okay. So it'd be 1/3 of, well, 10 meters per second squared. That's about 3 point something meters per second squared. Okay. You guys good? Again, your textbook said double, so all you have to do is apply factors of 2 instead of factors of 3. You can get your book number. Oh, this next question I like a lot. And this next question is the last question from your main set, number 94. How fast would a planet of Earth's mass and size, so basically Earth, have to spin so that an object at the equator would be weightless? Give the period of revolution of the planet in minutes. Ooh. So the premise is that, zoom out, it's number 94. Let's get a picture of Earth going and think, how's this going to play out? There's the Earth, equator, North Pole, South Pole, all that. Okay. The Earth is spinning west to east. Okay. I'm going to call that spin rate omega. Now, this was a new concept that you guys just learned a few days ago on Friday. You guys remember the way we usually think about speed or velocity is linear speed or linear velocity. That's like meters per second, miles per hour. Point of radar gun at it, read it that way. Okay. But the new way you guys learn on Friday is like a spin rate, like how fast is something rotating. Okay. And those are related to each other, but they're not the same thing, not the same units. Right? You guys remember these coins? Right? So both these coins right now have this exact same omega value, like the exact same radians per second, revolutions per minute. Right? But they have different linear velocities, right? The closer you are to the center, you're moving like slow linear velocity. The further you are, moving faster. Okay. Side thought, just to remind you guys how this is working. Okay. I wonder if you could get this planet spinning so fast that if you were right here at the surface, at some point you would just fly off the surface. Think that could happen? Now, would you fly off? Which way would you fly off? Would you fly off directly away from the planet, or would you fly off tangent to the motion? Tangent to the motion. You are right. With some value v, and you fly off into space. Huh. How fast do you have to get this planet spinning for that to happen? Of course, you guys know too, if you're up here with Santa Claus and the elves in the North Pole, you'd be safe, right? Because there's zero linear velocity up here. All right, well, let's see. Hey, do you think that, I have a hunch what the answer might be before we start. Because I remember a satellite in low Earth orbit, which is, a few hundred kilometers up, but in terms of the radius size of the planet, not hugely different from the radius size of the planet itself, proportionally. Does anybody remember how long it takes the International Space Station to go around the Earth once? It's about how many minutes? About 90 minutes, right? You guys remember that? Huh. And if you were inside the International Space Station, when you feel weightless, right? There's a weight that's the centripetal force, so you're in free fall, right? You feel weightless. Right? I bet that is sort of going to be the same answer as this. I bet the answer to this, how many minutes does it take the Earth to rotate once for you to fly off at the equator? I bet it's pretty close to 90 minutes. You guys think it's pretty close to 90 minutes? Okay. Let's find out. So what I'm thinking is that the centripetal force would be provided by your weight, right? And what are expressions for these? Now, the go-to formula for centripetal force we've been using for a long time is mv squared over r. Maybe r is the radial size of this planet. R. Okay. And then weight could be like mg. Okay. But you know what? If I'm more interested in this omega, maybe I actually picked the wrong expression for centripetal force. So we scratch that out. Okay. And let's try a new expression. Or how about this? Isn't v equal to omega r? Okay. I get rid of that. Okay. You guys remember how v is equal to omega r? Okay. That's to say, if you want to know the linear speed of the Roosevelt on the outside, you have to know the spin rate times its radial location from the center, right? And if you take that, if you take this expression and you substitute it into there, you can get the other formula for centripetal force that I showed you guys a few days ago, which is this, m omega squared times r. So maybe we should just scratch that out, just do a little substitution. At least you do the same spot. However you think of it, this is going to be one of the points in the process. So the centripetal force is only provided by your weight. Right? That's to say that there's no normal force anymore. So normal force goes to zero. Okay? Right? Yeah, but why does this work? Tell you guys a bit more about this setup, because the free body diagram for a person, I ran over here. Put this on the back. Okay. Free body diagram. Okay. For a person just at rest at the surface of Earth. Okay. Well, isn't there usually a weight pulling down and a normal force holding you up, and aren't those equal to each other in value? Okay. Except they aren't exactly. Weight is a little bit more than the normal force. Okay. Why is that? Well, because the net force is down just a little bit because you're on a rotating frame of reference. Technically, we're all accelerating towards the center a little bit because of its spin. Okay. But what if this normal force approaches zero because it's spinning so much? We fly off into space. That's what the setup is. Now, what's going to cancel out on both sides? You see the mass, right? Which might not be a huge surprise because that happens quite a bit in here. What that means is, hey, if you had a bunch of people lined up on the equator, maybe like small people, big people, they would, you spin up the Earth like faster, they would all fly off the surface at the same value because mass cancels out, right? Let's solve for this omega, and go ahead and plug in the other values while we're at it. So omega squared times radial size of the Earth is 6.38 times 10 to the 6 meters. That's equal to, and then g is just 9.8 meters per second squared. Right? So it looks like I'm 2 algebra steps away from solving for omega, like what's the spin rate of the Earth to make all of this happen, people flying off at the equator. So I got to divide both sides by the radial size of Earth. So what's 9.8 divided by 6.38 by 10 to the 6? And then square root both sides. So omega squared equals 9.8 meters per second squared divided by 6.38 by 10 to the 6 meters. Don't forget if you're plugging this in your calculator all in one go, that there's two different things multiplied together in the denominator. So make sure you group it together in parentheses, just like I have here. And then if you want to isolate omega, well, just take the square root. Ooh, this is a tiny number. This is 0.00124 radians per second. So apply the formulas, then what naturally comes out of that is some value that has to do with like radians per second. That's another reason that radians is a really good way to measure angles. I wonder how many degrees per second this is. You guys know how to convert from radians to degrees? There are two pi radians in a circle, but 360 degrees. So if you take this number and divide out the radians, 2 pi, and multiply back in the degrees, which is 360, okay? Or you could do divide by pi times 180. Okay? So in case you're curious, this is also 0.071 degrees per second. You guys know what 1 degree is. That's, do you have a protractor? Oh, protractor. You guys know what 1 degree is. It's one of these little tiny tick marks. So 0.07 of that every second. So if you're watching this from space, say if you're on the moon, it might look like the Earth was spinning really slow. Like to get to the point where people are flying off, might be kind of hard to tell if the Earth was even spinning. Okay. That is the answer to the question, how fast does the Earth have to spin? But there was another part of the question, and the other part was, well, how long would it take to spin around once? And I had a hunch that it's probably close to that satellite situation of about 90 minutes. You guys want to see how close to 90 minutes it is? We could solve this. Here's one way to do it, is with a dimensional analysis table. Or I guess you could do angular displacement equals omega times t. You could do it that way too, but I'm going to solve it this way. So 1 revolution. Okay. I need to convert this into how much time, and I'm going to use this rotation rate as a conversion factor. So I know that 1 revolution is 2 pi radians. Okay, great. So now I've got it in terms of radians, so I can bring in this conversion factor. 0.00124 radians per second. Notice I put it upside down, that fraction. But by doing that, now the radians cancels, and I have a time needed. Awesome, because the question was how much time does it take to run? But your book said one more thing. It said to put it in terms of minutes. So let's do that too. 60 seconds per minute. Now the seconds cancels, and the only unit left on board is minutes. So this will tell me how many minutes would it take the Earth to spin around once at this crazy fast speed. So you got 2 pi, that's the only thing in the numerator, and then divide by, got 0.00124 and 60 in the denominator. This is looking like, oh, look at that, 84.5 minutes. That's about 90 minutes right there, isn't it? Yeah. So if the Earth spun around once every about 84, 85 minutes, and you were standing at the equator, you'd be flying off the surface. You'd feel weightless, just like in the International Space Station. That's it. Yeah, if you were on the moon watching this whole process happen, it would take about almost an hour and a half for the Earth to spin around. But at that rate, people would be flying off at the surface. I'd have some trees from the Amazon rainforest into space. All right, you guys ready for, make sure, oh, one more thing before we switch over to Kahoot. I want to tell you guys about O'Neill cylinders. O'Neill cylinder. Because this came up in my AP class. It's going to come up here anyway, but I want to introduce this idea to you. Okay. And that's, if you make a giant cylinder and put this in space and have it rotating about this central axis. Right, here's the center. Right, this whole thing's spinning around with some omega value. Right. Now, if this is in deep space, there's no real gravity, right? I mean, there's tiny amount of gravitational forces maybe, but there's no planets or anything nearby. Okay. But if you have this ring spinning, do you think you'd be walking around on the inside and it would feel kind of like there was gravity? guys can imagine that? And on the underside, maybe all these people feel like they're standing right side up. And if this thing is big enough, has some radial size r, it might be really hard to tell the difference between real gravity and fake gravity, right? Hey, what if I tell you how big this is? Let's call it 500 meters radius, 500-meter radius, so 1 kilometer diameter. I wonder how fast you'd have to spin this, omega, so that everybody walking around on the inside feels like there's Earth gravity, 9.8 meters per second squared. Do you think that there's a certain rate you could spin that? You could solve for? Okay, you think you can figure that out? Huh, let's do that. So centripetal force, well, you know it's mv squared over r, but you also know m omega squared times r. And so you know that, so throw that expression down. Okay. I want to know how fast you have to spin this so that the gravity force feels like your weight. Okay, so this is going to simulate this. Right? Now, there's no real gravity, but there could be fake gravity. You could perceive this, basically, right? Oh, isn't your mass going to cancel? Whew. Well, that's good, because now all these people walking around the inside would require the same spin rate to experience the same gravity field, even though fake gravity, I should say. Okay. Let's pop in some numbers. So if I want this to be 9.8 meters per second squared, I got omega, trying to solve for that spin rate. And what's the radial size of this thing? Oh, I told you 500 meters. So you guys see that the radial size is definitely important. So different size O'Neill cylinders would have to spin at different rates to get the same effect. Going to divide both sides by 500 and take the square root. Just like that. This is 0.14 is the number, and the unit attached to that is radians per second. 0.14 radians per second. Which, by the way, times 180 over pi is about 8 degrees per second. So, yeah, you know, if you were out in space watching this, you know, independently of this, you know, maybe from the station watching this thing, yeah, you could watch that rotate about 8 degrees per second. I would definitely see that rotating. Okay. I wonder how long it would take to rotate once. Let's do this exact same math that we did before, except I'm just going to change the rotation rate right here. Okay. So to rotate once, I'm going to take the 2 pi radians it's going to turn, divide by 0.14 radians per second. Okay. It would take about 44.9, let's call it 45, about 45 seconds to turn around once. So if you have an O'Neill cylinder that's 1 kilometer in diameter, 500 meter radius, and it rotates completely in 45 seconds, then that means that if you're walking around the inside, you would feel like there was Earth gravity. It'd be kind of hard to tell the difference. Right? You guys got that? All right, you guys got your phones? Almost ready for Kahoot? All right, so switch over to the computer. I'm going to show you guys a quick video of what I was just talking about, and we'll do one of these one day too. There's here we go.
What device?
No, that's right. Thanks, sir. Did anybody happen to see a movie called 2001: Space Odyssey from the 1960s? So this is a clip from that movie. Hey, that's an O'Neill cylinder, isn't it? And if you're walking around on the inside, then it might feel kind of like you were standing on the planet. There you are. And what does it look like inside that thing? Well, maybe not that particular one, but maybe a similar one. So let's go inside. Ooh, I see this guy running around this O'Neill cylinder. Now, of course, this is just 1960s special effects. He's not really in space in an O'Neill cylinder, but it would look like this, wouldn't it? Ooh, just like this. I can tell you guys too that particular size O'Neill cylinder that guy's in is pretty small, and they would have to be spinning how compared to my example? Really fast or really slow compared to my example?
Real fast.
Yeah, real fast, right? Because it's real small, so it's spinning pretty fast. And there would actually be a noticeable difference between his head and his feet in terms of artificial gravity, and the physics would be like noticeably wonky. But if you had a big enough size O'Neill cylinder, then it might be kind of hard to distinguish the difference. All right, so that. All right, let me switch this. And I got this Kahoot lined up, ready to go. These are all going to be on gravitation related questions. The questions up here, you guys had printed out, I think from last week. There's some paper, I think I gave you guys a week or two back that should have these questions printed on it in case you wanted to follow along. That's easy. All right, so if you're about to hop in, then that 6-digit PIN will be at the bottom of the screen. Okay, and here we go. Newton hypothesized that the moon Yep, all true statements. All right, nice going. So, before Newton, everybody did know that the moon revolved around Earth, but Newton was the first guy to figure out these things, right? That there's gravitational attraction, the moon's falling around Earth into orbit. Yeah. All right, so Cheyenne, Michael, Tricia, Chris, and Carter, they're on the board. If the mass of Earth increased with no change in radius, what would happen to your weight? Your weight would also go up if the mass of Earth increased, right? Here, I'll go ahead and flip the screen for this one. Okay. So you guys know weight equals G-M over radial size squared. Okay. So here, planet, radial size R, okay. Staying on surface, M, right, all that stuff. You guys remember this? Okay. So they're saying, well, what if you just pump up the mass of the Earth, but leave everything else over here saying? In fact, if you exactly double this mass, doesn't your weight also double? Right, double. That's a direct relationship, isn't it? You guys that? Now, the question that's about to come up is looking at these two, this inverse square relationship. You guys ready for that? So as R increases, but if you left the numerator the same, as R increases, what happens to your weight? Gotta see who's about to get that. Hopefully everybody. Oh, Tricia, moving to the top. Michael, Emily, Kaden, and Cheyenne. There you go. Oh, if the radius of the Earth decreased. Like all else equal. Ooh. So basically, if you take the Earth and just like crunch down, you're staying on the surface. What's happening to your weight as the Earth gets crunched down? Yeah, your weight would go up. Right here. Let's pull the screen back over. Let's play around with some numbers. They got some crazy numbers here. What is guys tell me, what is 24 divided by 12? 2. Okay. What is 24 divided by 8? 3. What is 24 divided by 6? 4. Okay. So I'm leaving the numerator the same, just like that question. The numerator was the same. Okay. But see how the denominator is getting smaller? But doesn't that blow up the overall fraction bigger? That's called an inverse relationship, right? So one gets smaller, the other gets bigger. Right? So yeah, if you took the Earth and just like compressed it down, like just smash it, And some guys along the right of the surface, you actually would be getting heavier and heavier during that process. That's what that means. Trisha still in the lead. Got Michael, Carter, Emily, and Caden. The gravity force between two massive spheres is yeah, those are all true statements. Attraction, proportional to each mass, inverse square relationship to the distance, right? Trisha on fire. Carter, Caden, Michael, Emily, jockeying in fourth position. Two objects move toward each other. As the objects get closer and closer, what happens to the gravity force between them? See, like two asteroids floating around, start to pull together. Yeah. Okay, let me pull up the screen. About half you guys got that. That's awesome. Yeah, the gravity force does increase. So, here, I've got these two asteroids, M and M, or the masses, and the center to center distance, I'll call it R. Got our old classic frog face. And the gravity force, we draw the gravity force between them. So this is straight. This gravity force, which is equal and opposite, I mean, it's the same force, even though there might be different masses, is equal to G(m)(m) over R squared. Hey, this is the old, the whole example I was doing with these fractions over here also applies, doesn't it? Okay. So see how as this radial, as the center to center distance R between them gets smaller, 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 the denominator gets smaller, the numerator stays the same. So doesn't the force get bigger, 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 right? Same thing as these fractions here. As the denominator gets smaller, the overall fraction blows up bigger. Trisha keeping the top spot. Got Austin hopping in. Suppose gravity force between two spheres is 100 newtons. If the distance between those is doubled, so getting further apart, the gravity is getting weaker. If you double the distance, you guys remember something called inverse square law? Inverse square law? Ooh, there's one winner. One. So, I'm just going to point this out with exactly what we got right here. Okay, so suppose this whole thing comes down to like 100 newtons. 100 newtons, what we're looking at. Okay. But what if you, say, did the opposite last one? What if you push these like twice as far apart? Right, so I'm going to throw a factor of 2 on this R. Hey, doesn't that factor of 2 also get squared? What's 2 squared? 4, and it's 1 over that because it's in the denominator. So the new force is a fourth of the old force. And if the old force was 100 newtons, the new one's 25 because it's 1/4. It's 1/4 of 100 newtons is 25 newtons. What if you got that? Ooh, not one of those 5. Somebody. Force of gravity on you is greatest when you're standing. Remember there last week we tumbled into the center of the earth and then took off in a rocket ship? Where did you weigh the most on that graph? Make a whole graph about that. I see it in your notes. Okay, some of you guys remember that. I'm gonna sketch this graph out real fast. Okay. So the story went like this. Okay. Got planet, guy at the surface brought his shovel, and he tunnels into the center of the earth. Okay. Versus maybe some other guy takes off in a rocket and it's like flying around. Okay. So what's the gravity pull on you as a function of your location? Maybe the, okay. So some general value R. Okay. What is your weight well, gravity force. Okay. And then we got the surface of the planet at that exact location there. Okay. So at the surface, your weight is gmm over radial size of the planet squared. Okay. At the center, it's 0. There's a direct relationship all the way down the spiral tunnel. And then if you take off in a rocket, the gravity force from the planet decreases with an inverse square relationship. Yeah, so the most you ever weigh is right here at the surface. That guy right there. Tunnel down, your weight goes down. Get further away from the planet into the sky, your weight goes down. All right. Got Trisha, Caden, Michael, Carter, and Olivia. Lunar month, about 28 days. But what if the moon was closer to us than it is now? Which it has been in the past. The moon is very slowly drifting away from the Earth. So, say back about 60 million years ago, when the moon was closer. Yeah, less than 28 days. You guys are right. You guys remember orbital speed? Square root GM on R. Hey, how about low Earth orbit satellites? Those take about 90 minutes to go around. You guys know that. Okay. And also, satellite speed and time period is independent of the mass of that thing. Yeah? So, yeah, you guys are absolutely right. Closer the satellite is, faster it's going to go around, less time period. Trisha, Carter, Caden, Michael, and Austin. 400 Newton woman stands on top of a tall ladder, so she is 1 Earth radius above Earth's surface. How much does she weigh? Give you guys a hint. Aren't you effectively doubling your distance from the center of the Earth? And taking consideration of inverse square law, right? So if you double your distance, 1 over r squared, what happens to your weight? Oh, yeah. You guys got that. Okay. So sketch this out. So you're on the planet, you weigh some amount, but what if you took a ladder into the sky? And this ladder was also r distance long, right? You go to the top of this ladder. Okay. Well, your weight, gravity force from me, right, is gmm over distance squared. And haven't you effectively doubled your distance from the center, from here to here? Factor of 2 squared is 4, that's 1/4. So your new weight up here is 1/4 of the weight down here. If you weighed 400 newtons at the surface, you only weigh 1/4 of that up in the sky, not sky ladder. Doubling your distance. Oh, I saw Carter was on fire, Trisha's still in the lead. Suppose gravity force between 2 spheres is 100 newtons. What if you cut that distance in half? Now, still an inverse square relationship. I bet the force is getting stronger, right? Getting closer. Right. You know what? Right. So force between these two things is 100 newtons, and you cut that force in half, or sorry, the distance in half. Right? So it looks like the force should go up by a factor of 4 to 400 newtons. I don't have to write anything new because that is also exactly this picture, right? So got 2 massive spheres, like the planet, and well, I guess this person's like a massive sphere. So this distance is well, right here, that distance, right? So the gravity force was 100 newtons. If you cut that distance in half, see the force goes up to 400 newtons. So it's still the inverse square law. Throw a factor of 1/2 here, half squared, 1/4, 1/4, 4 times the gravity force. Same thing. Trisha on fire. Michael, Carter, Austin, Olivia. According to Newton's laws, a rocket pebble will fall with the same acceleration because, remember the 2 kids on the island trying to get the Hershey bar? This is that story. Hey, gravity force. Is that called weight? Is the weight the same? No. Is weight divided by mass the same? That ratio is the same for all objects at the surface of some planet. Whoops. I gotta speed along a little bit, make sure I beat the bell here. Acceleration due to gravity. GM over R squared. Capital G M over R squared, right? Yeah. All those go into it. Patricia, Michael, Carter, Olivia on fire, Austin. Gravity field strength at the center of the Earth. I said, if you're right at the center of the Earth, I drew you guys a graph a few minutes ago. It said at the center of the Earth, you weigh 0 newtons. Remember, every single grain of sand is pulling you in a different direction, so all the gravity cancels out. Yeah. Where would the floor even be at the center of the Earth? Yeah, you'd be floating around like an astronaut at the center of the Earth. If the sun were to collapse into a black hole, what would Earth do? I guess the key here is that, does the mass of the sun change turning into a black hole? Does mass change? No, it doesn't, right? So does anything in the equations change? Huh. Well, yeah, besides being very dark. Yeah, besides that. Yeah, so the premise here is that according to all the gravity equations we've done, gravitational force, orbital velocity, all that, nothing changes in the equations. Right? So mass is concerned. Ooh, Trisha's on fire, getting some more points. Maybe this would have been a better question first. When a star does collapse into a black hole, what happens to its mass? Somebody earlier, by the way, pointed out that our sun is not actually big enough to collapse into a black hole. I think you need something like 3 or 4 times bigger than our sun, something like that. Okay. But mass is conserved. You guys knew that from chemistry. Conservation of mass. Ooh, Trisha's still on fire. Tidal forces. There must be a relatively large distance between what and what. I haven't talked about this. All right. Yeah, opposite sides of the body experiencing the tides. Okay. Now, I haven't talked about this at all. So let me show you guys what to talk about. What do you think there's a greater force from on Earth? Do you think there's a greater force from the sun or from the moon? Yeah, from the sun. But what's the main driver of the tides? The moon. Wait, how is that possible? It has to do with proportional distances between, either the sun and moon and opposite sides of the Earth. So for the sun, say I'll call this D2 and D1. Okay. D2 over D1 is pretty close to a 1-to-1 ratio. I mean, it's a little bit more than 1, but it's pretty much 1. Okay. Versus for the moon, if you go from the moon to the far side of Earth, or the moon to the close side of Earth, call that like a D4 and D3. D4 over D3, well, that is definitely bigger than 1. Okay. And, well, it's also definitely bigger than this ratio, which is a tiny, tiny bit bigger than 1. Okay. So, this causes tides. This is the tidal effect. You guys have ever heard of a tidal locking? You guys know how the same side of the moon always faces the Earth? The moon is tidally locked to the Earth because its mass is distributed a little bit unevenly. Right? That's actually a pretty common thing in the universe for tidal locking. If the radius of the Earth were half of what it is now, what would be the value of G? I'll tell you guys this. So if you cut the radial size in half, G is going up. It's an inverse square relationship. Isn't it 1 divided by a half squared? Right? GM over R squared. So what's 1 divided by a half squared? That's a factor of 4, right? What's 4 times 10 meters per second squared? Is that like 40 meters per second squared? Right? You guys get that? So a factor of 4. Oh, look at you guys. Yeah. All right. 3 questions left. A circle is a special case of, you guys get 5 seconds. An ellipse. Oh, yeah. You guys remember making those ellipses last week? If you take the 2 focal points and put them on top of each other, you can have a circle. Object is placed exactly halfway between the Earth and the Moon. That object will fall toward the Earth. Yeah, because Earth is more massive, so have a greater gravity force. Right, and for the wind, I suppose there's a communication satellite that seems to be hovering over the same point on Earth's surface just indefinitely. You're sitting on Earth, at the equator, you look up, you see a satellite. It looks like it's hovering there. How? Because the orbital period of that satellite would be 24 hours, which would exactly follow the rotation of the Earth. Yeah, that's called a geosynchronous orbit. Geosynchronous, or sometimes called geostationary. Right. With the bronze, Carter. With the silver, Michael. And the gold goes to Trisha. Hey, nice job, guys. We got some runners up, Kaden and Emily. You guys may have noticed too that a lot of those questions were on your Open Notes take-home quiz, so that'll help you guys out there too. All right, Bill, in 10 seconds. That worked out perfectly. Right, so if you're taking a PSAT tomorrow, good luck on that. If you saw the question where you're supposed to be, then let me know. And